Hey everybody, it's Miss Maneely, and I'm going to give you a quick review of polynomials in order for you to prepare for our test on Friday. In the very first one, you're given a polynomial. Note that it is written so that 3x squared minus 4x to the 6th minus x plus 2, that is not in standard form yet. It's almost there because we are looking at adding and subtracting power terms, but we have to make sure that we write the equation in standard form before we answer any of the questions. So remember, when we're writing in standard form, we want to make sure that the term that has the highest degree comes first, and that would be the negative 4x to the 6th. And then we want to move to the next highest exponent, and that's going to be plus 3x squared. The next would be my x term. Note the sign in front of x is negative, so I want to make sure I keep it there. And then my positive 2 on the end. Now the equation is in standard form. And if I want to find the degree, well, when the equation is written in standard form, the degree is really easy to identify. It's just going to be the highest exponent. And note that that is an even number, and that's going to help us when it comes to graphing. In letter B, it says to state the lead coefficient. The leading coefficient would be the coefficient of my leading term. My leading term is this whole thing, is the whole expression, negative 4x to the 6th. The coefficient, remember, is just the number in front. So it's the negative 4 would be the coefficient, and that is negative. The constant. Remember, we've got variables and constants. Variables obviously vary. If you enter different numbers into the variable, it's going to change the value of the quantity. But a constant will not change. That means it can't have a variable next to it. So in my equation, 2 is the constant. Then it says to state the end behavior using proper form. And what this means is, this is the statement where we talk about as x approaches, and if we think about the left-hand side first, we'd be saying as x approaches negative infinity, what's going on with y? We got to figure that out. And we also have the statement as x approaches positive infinity, where is y going? What's happening to the graph? Well, it's hard to do that off the top of your head. It really, I think, helps to draw a picture. So I know that I have an even degree polynomial. And so one of the things you'll have to remember, if we're looking at the degree, we can make ourselves a little bit of a table. We've got even degrees. Let me do even first. And we have an odd degree. If we look at the sign of the leading term, or the sign of the coefficient of the leading term, it's either going to be positive or negative. And that'll help us to know whether or not our function is going to be ultimately increasing or decreasing. Well, if it's an even degree, that means that the ends are going in the same direction. If it's positive, it means that they're both going up. If it's negative, that means they're going to both be going down. If it's an odd degree, that means it's going to look like that S shape where the ends are going in opposite directions. So think odd, opposite. If the sign of the leading coefficient is positive, that ultimately means it's going to be increasing to the right. And if it's negative, it's going to be decreasing to the right. So these graphs are what I would call long-run behavior. What the graph would look like from very far away. The end behavior is described by these statements. And so if I know that I'm dealing with an even degree that has a negative leading coefficient, then that means that I'm thinking about this graph. Both ends then are pointing down. And if I think about what's happening on the left-hand side, I can see the graph is going down to negative infinity, and on the right-hand side, the graph is going down to negative infinity. So it will help when you're asked to write the end behavior to sketch a picture first. And also, if you sketch a picture and you sketch the wrong picture, but your end behavior is correct for the picture you sketched, then I can sometimes give partial credit for that. On the quarterly tests, if they're worth 1 point, obviously I can't, but on some of the tests that I give, if you're showing your work, then it helps me see where you're making mistakes, and I can award partial credit if that's possible. Problems 2 and 3 also deal with end behavior. So here we are in number 2, looking at the graph of a polynomial. Notice that both ends are pointing in the same direction. Since they're both pointing in the same direction, that tells me that I'm dealing with an even degree polynomial. And since they're pointing down, that tells me that my leading term is negative. And so if I look at my options, that means I know I can cross out anything that deals with an odd exponent. And since I know that the leading term must be negative, that corresponds to letter D. In number 3, the reason that we used the letters A, B, C, and D instead of numbers is because it's really important that you understand the behavior of the graph without using your calculator. So if we do it this way, you can't type the equation into your calculator. And I know that sounds like we're trying to trick you, but it's not. Remember that it's the leading coefficient that determines the behavior of the graph. So all of these equations, the one thing you do want to double check is to make sure that they're in standard form. And in each case, they are. So I'm just going to highlight the leading term. And I know, remember, if it's got an even exponent, that's the number that's being raised to the power. If the exponent is even, then I know that the ends are going in the same direction. If the exponent is odd, then I know they're going in opposite directions. So if I look at the first one, I've got negative ax to the 5th. We have an odd exponent, which means that the ends are going to go in opposite directions. It's going to have that S-shaped graph. I also can see that the leading coefficient is negative. That must mean that my graph is going down. So that's going to correspond to to number 4, to the 4th graph. Ax to the 3rd, my next one, again I have an odd exponent, so again I'm dealing with odd behavior, but this time the leading coefficient is positive. That means the graph must be increasing to the right. That's going to be the second one. The next two both deal with even exponents, so I'm dealing with graphs that are going to be going in the same direction. The third one, we have a positive leading coefficient, and so that means that my ends must be going up. And that's going to correspond to number 1. And number 3, since I have a negative leading term, I know that it's going to mean that both ends go down. And that's going to correspond to graph 3. Okay. In number 4, notice you are given a polynomial in factored form. So please make sure that you know the difference between standard and factored form. Standard form, we're adding and subtracting. Factored form, we're multiplying. And so in letter A, it says to state the roots and their multiplicity. Remember, the roots correspond to our x-intercepts, or the zeros of the function. And if you think of them as zeros, it might remind you that ultimately what you're doing is taking each of the factors and setting it equal to 0, and then solving for x. So if I do that with x minus 5, that means that x is going to be positive 5. That's why it's always opposite. My exponent here, if I'm thinking about this factor, the factor is in parentheses, there's no exponent, so that actually means that there's one factor, which tells me it's single. It's a single root. The next quantity, we've got x plus 4. I'm going to set that equal to 0, and that tells me then that x is equal to negative 4. Since that quantity is being raised to the 2nd power, it tells me it's a double root. And the last one, x minus 2, when I set that equal to 0, I find that x is 2, and again, the exponent is 1, and I know that because I don't see it. That tells me it's a single root. So if I want to know the degree of the polynomial, the degree, and I spelled single wrong, I'm not sure how I managed to do that. Sorry. So the degree of your polynomial should correspond to the number of factors of x. So if I look at my quantity, this is where you have to add them all up. When it's in standard form, the degree is really obvious. It's just the highest exponent. But when it's in factored form, you have to count up all the factors of x. So I can look at the roots, or I can just look up at the equation itself. Like this is one factor. This is another factor, but since it's being squared, it counts twice. So this is 1, 2, 3, and then my last one counts as a 4th factor. And so I know my degree is 4. And so if I know my degree is 4, notice that there's no number out in front. There's no, the leading coefficient in this case would just be a positive 1. So that means my leading term is positive, or my leading coefficient is positive. So if I have an even exponent, an even degree, and a positive leading term, that means I'm dealing with two ends that should be going up. So if I'm asked to state the end behavior, what I've just sketched is what I call the long run behavior. The end behavior is that statement. As x approaches, and we'll always start on the left first, so negative infinity, I know that y, in this case, is going up to positive infinity. And as x approaches positive infinity on the right, y is also approaching positive infinity. Now it says to use the information in parts A, B, and C to construct my graph. Well, I know where the x-intercepts are because I know my roots. I know I have a root at 5, so I'm just going to mark my x-axis. And I know that I have an x-intercept at 5. So 1, 2, 3, 4, 5. I have a root at -4. And I have a root at +2. And I know from far away, my graph, my ends and both sides need to be going up. So that's going to help me when it comes to sketching the graph here. So the first x-intercept, if I'm moving from left to right, the first x-intercept I come to is -4. And notice we said -4 is a double root. That must mean then that my graph turns around at that point. It doesn't cross the x-axis at -4. It just bounces off. So my graph has to turn around in order to come back down to hit +2. And +2 is a single root, so I know my graph has to pass through that. And then it must turn back around to hit +5, which is also a single root. So again, it's going to pass straight through that. And so that's what the sketch would look like. Number 5, this has to do with factoring. And so I'm going to review some of the factoring rules that we talked about today in class. The first thing you always want to do is factor out a greatest common factor. So if I look at letter A, the easiest way to do this is just to look at if you have a coefficient in the first term. In this case, I have a 2. If I have a greatest common factor, it's going to have to be a 2 or an x. And so if I look at the rest of my numbers, I can see really fast that 2 does not divide into 5 evenly. It doesn't divide into 45 evenly, so I can't pull a 2 out of every term. I also don't have an x in every term. So I don't have a greatest common factor initially. Like I don't have it if I'm looking at all 4 terms. There's nothing that I can do to simplify that way. So that's the first step in factoring. There's nothing for me to do though. So now I'm going to move on to step 2, which tells me to count the number of terms. I have 4 terms, and anytime you have 4 terms, you're going to scoot to grouping, the grouping method, where you're going to look at the first 2 numbers and the last 2 numbers, and then you're going to just look for the greatest common factor in those pairs. So if I'm looking now just at the 2x cubed minus 5x squared, I'm going to first look at my numbers. And 2 and 5, they have nothing in common. I can't divide the 2 out of 5 and get a whole number. So I can't factor out any numbers, but they both involve an x. In fact, the first term has 3 factors of x, and the second term has 2. So I actually can factor out an x squared. And I'm going to use the division symbol because that's essentially what I'm doing, but I'm undistributing. So if you think about your distributive property, I'm now going to move the x squared out in front, and then I'm going to write what happens when I divide out the x squared. So when I do that, if I have 2x cubed divided by x squared, well, that's like having a 1x squared, and 2 divided by 1 is just 1, or I'm sorry, 2 divided by 1 is just 2. And then if I have x cubed divided by x squared, I'm essentially pulling away 2 factors of x, leaving me with 1. And then I have minus x squared divided by x squared. So 5 divided by 1 is still 5, and that's going to be a -5. My x squares ultimately cancel to 1. In my next pair of terms, I've got a -18x and a +45. So I want to think about what number goes into both of those terms. I also want to consider the fact that the 18 is negative. I'm actually going to use that in my greatest common factor. Now 18 and 45 can both be divisible by 9. So I'm actually going to divide out a -9 from both terms. And again, just like I did with the x squared, I'm going to move that -9 out in front, and then I'm going to write what I have left. So if I have -18x divided by -9, I'm left with 2x. +45 divided by 9 leaves me with a -5. And now notice these quantities are the same. So I'm basically, they become my greatest common factor, and I factor them out in front. And so when I do that, I'm going to write this over here. I'm going to have 2x minus 5, and then what I have left is x squared minus 9. But you need to be careful because x squared minus 9 can still be factored. As long as you still have a power with your x, you want to think whether or not you can break it down any further. And in this case, since I have x squared minus 9, these are both perfect squares. The root of x squared is x, and the root of 9, the square root of 9, is 3. So using my difference of squares pattern, that's going to be x minus 3. x plus 3. And then I'm still going to bring down the other factor of 2x minus 5. So in completely factored form, I've got 2x minus 5 times the quantity x minus 3 times the quantity x plus 3. I have 3 factors of x, which corresponds to my degree of 3. And so I'm done. Letter B. I've got g of x is equal to x cubed plus 64. Well, as soon as I see the x cubed and I only have 2 terms, I know this must be the sum of cubes. And the sum of cubes basically says if I've got a cubed plus b cubed, I can break that down to a plus b times a squared minus ab plus b squared. So the idea then is to figure out what a and b are. And a and b are simply going to be the cube root of both of your terms. So the cube root of x cubed is going to be x. And be careful with the 64. 64 is also a perfect square. But we're taking the cube root of it, and the cube root of 64 is 4. So that gives me my a and my b. And now I'm just going to fill in the formula. So I'm going to have a quantity of a plus b, which is going to be x plus 4. And then I'm going to have a trinomial of a squared, which in this case would be x squared, minus ab, which will be minus 4x, plus b squared, which would be plus 4 squared, which is just 16. And remember that second parentheses, that trinomial, cannot be factored. It actually is going to correspond to imaginary roots, and you would need the quadratic formula to break it down. That's as far as you can go in letter B. And notice that I have one factor of x here, and this factor is of degree 2, so it counts twice. So that means that I have all 3 factors of x. In letter C, we have h of x is equal to 2x cubed minus 4x squared minus 30x. And again, the very first thing I want to look for is something in common. Since there's a 2 in front of my x cubed, I want to see if I can pull a 2 out. I've got a 4 and a 30, which are all divisible by 2, so I'm going to divide out the 2. Now let's pay attention to the x. I've got x cubed, x squared, and x. Each of those terms has an x in common, so I'm going to divide out the x. Now, the 2x doesn't disappear. It actually is just being factored out. I'm like undistributing it, so it's going to go out in front. And now I'm going to divide everything by 2x. So 2x to the third divided by 2x, my 2's cancel. If I have 3 factors of x and I'm taking one away, that means I've got 2 factors of x left. In the second expression, negative 4 divided by 2 is going to leave me with negative 2. And x squared divided by x, again, if I have 2 factors of x and I pull one out, that means I've got one left, 1x. And negative 30x divided by 2x, negative 30 divided by 2 is going to give me negative 15, and my x's cancel. So since I still have an x squared, and this is not a sum or difference of cubes, I'm going to see if I can factor that trinomial any further. So now that I have 3 terms, this brings me to my product sum method. And I'm only focusing on this expression within the parentheses. My product in this case would be negative 15, and my sum would be negative 2. So I'm looking for numbers that multiply to give me negative 15 and add to give me negative 2. Let's try negative 5 and 3. That now tells me what needs to go in the parentheses when I factor. The 2x is going to stay where it is. It's going to hang out. But now I'm going to factor that trinomial into an x minus 5 and an x plus 3. And if I add up all my x's, I've got 1, 2, 3, which is exactly how many I need. In letter D, we didn't get to look at any examples like this, so I'm going to make this extra credit on the test. But notice how it's x to the 4th plus 6x squared plus 8. We've seen this pattern before. What about if I wrote it as x squared plus 6x plus 8? If I wrote it like this, you'd recognize that there are 3 terms. Sorry, I'm going to move that up. And so I'd use the product sum method, which means that my product is 8, my sum is 6. And I think about numbers that multiply to give me 8 and add to give me 6. I would say 4 and 2. And so basically I would have x plus 4 times x plus 2, and I'd be done. But I don't have x squared plus 6x plus 8. I have x to the 4th plus 6x squared plus 8. So I just have an extra factor of x. So all I do is write x squared plus 4 and x squared plus 2. And even though in the first set of parentheses I'm dealing with perfect squares, x squared and 4, because I'm adding them together, I can't actually factor them. X squared plus 2 can't be factored either because it's not a difference of squares. So let me write not difference of squares or cubes. If it was, then I'd be able to factor it a little bit further. But this is as far as I can go with this problem. Okay, number 6. We've seen this problem before, and I put it back on the test because this is going to be on your midterm, a problem similar to this. It says Sam and his friends love skeet shooting, where they throw clay plates into the air and attempt to break the plates by shooting them with plastic BBs. Suppose f of t is equal to negative t squared plus 13t plus 4, and that represents the height and feet of the clay plate, where t represents the time in seconds. And g of t is equal to 4t plus 4, and that represents the height and feet of the BB plastic pellet. The plastic pellet follows this linear path for the domain of 0 to 12 seconds. This is on the non-calculator part of your test, so it's important that you understand how to do it. We're asked to find the time after the initial launch that the BB hits the clay plate. And if you think about it, the BB is going to be following the path of a quadratic because it's got the t squared and it's negative, so it's going to be going down. I know that my bullet or my pellet has the shape of a line from 4t plus 4. So it's going to look like this. And so I'm going to expect my graphs to intersect in 2 places. But since I'm only interested in the time after the initial launch, and we'll assume that this is when time is 0, and that's the initial launch, what I'm really interested in is this value here, where they intersect again. And the way to find that intersection is simply to set the 2 equations equal to each other. Negative t squared plus 13t plus 4, and set that equal to 4t plus 4. This is now just a quadratic equation. It's a type of polynomial, but it's one that we did in the last unit. To solve it, we need to get all the terms on one side and 0 on the other. So if I subtract 4t from both sides, I can also subtract the 4 from both sides, and that'll help me get this in standard form. I'll have negative t squared. 13t minus 4t is going to give me plus 9t. And 4 minus 4 is just 0. So I have negative t squared plus 9t, and that's going to equal 0. So I want to write this in factored form so I can solve it. And this is not one of my typical patterns, but the very first thing that we want to do anytime we're factoring is look for a greatest common factor. And in this case, I have a t in common. And since the leading coefficient is negative, I'm actually going to want to divide out a negative t. And when I do that, I'm going to be left with a positive t minus 9, because I'm basically dividing out a negative t. And that equals 0. And so to solve, I'm just going to set both parts equal to 0. So negative t equals 0 and t minus 9 equals 0. Well, if negative t equals 0, then positive t is going to equal 0 if I divide by negative 1. And if t minus 9 equals 0, that means t is equal to 9. And t is time, and it's measured in seconds, so you do want to include units. And since we're only interested in the time after the initial launch, I'm not really worried about that solution. There's 2 solutions here. I'm not really worried about the first one because that's the initial launch. What I'm worried about is the 9 seconds, because that's where the BB is going to hit the clay plate. And I think that's it. Oh, one more. So in number 7, this has to do with graphing parent functions and their transformations. So you're given a function f of x, you're given the graph, and then you're asked to determine which of those listed corresponds to the graph of f of x minus 2 minus 1. So you do have to remember how a, h, and k affect the graph. The number inside the parentheses with x is going to correspond to your h value, and it's always going to shift your graph left and right. The number on the outside here, that minus 1, is your k value, and it shifts the graph up and down. Okay. Notice that the coefficient of f of x is just a positive 1, so I don't have to worry about reflecting the graph or stretching or compressing it. I'm basically going to take this picture. Oops, I went a little too far. And if h, in this case, remember, we have to consider the opposite. So if it's x minus 2, that means that h is actually a positive 2. And so if h is a positive 2, I need to shift my graph to the right 2 units. So I'm going to do it like this. The minus 1 on the end tells me that I also need to shift my graph down 1 unit. So that's where what I've drawn in green is essentially the graph that I'm looking for. And there's only one that comes even close, and that's letter A. Now I think that is it. Yep. All right. Well, good luck to you. I hope this was helpful. If you have any questions, please come ready to class with them. I would love to see you in Bulldog Block. Like I said, on Thursday morning, I'm going to run all Bulldog Block is just going to be Algebra 2 review. So I hope to see you there.